Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. Today, we are going to introduce something very important, a very important concept in linear algebra, which is called vector space or vector spaces. So, what are vector spaces? Vector spaces, by the way, may be vectors, may be matrices, maybe polynomials, maybe many things if and only if they uh, have the following properties or the following axioms. Most importantly, in fact, we can divide them into like 5 additive and 5 multiplicative axioms. So if we start with the additive ones, the first one, which is very important. So first of all, we are going throughout this, we are going to say that, let's say, um, u, v, if I use u, v, or w, these are vectors and they belong to a vector space I'm going to call V. And if we are going to use letters like A, B, and C, these are real numbers, so they belong to the real class. Okay, having said that, we say that the first axiom we think about, which is so easy, is called closure under addition. Closure, what does that closure means? It means like you are imprisoned, okay? No matter what you do, you cannot escape out of the vector. So if I say u plus v, if I add two vectors in the vector space, they have to still be in the vector space. If they don't, then cannot be considered as a vector space. And then very similar like things like when we say they have to be commutative, meaning if I say u plus v, it's the same as I say v plus u. Okay? They also have to be associative under uh, the associative property means that if I have like 3 vectors, we said u, v, and w, and I have u plus v, and then I take their sum and add it to w, it is the same thing as if I take u by itself and add the summation of v plus w. Oh my God, I'm sorry. I think I'm getting a phone call. Oh, it's connected to the, okay. Um, okay. Then what do we have? So we did 3 of those, right? We also have, that's very important, the 0 vector. There is a vector called the 0 vector, just zeros. So if it's a matrix of zeros. If it's a polynomial, again, I have to have a 0 for that to be a vector, okay? And the 0 vector, if I say u plus 0, I get back u. So it doesn't change the vector. If you add it, you get back the vector and you say, that common sense. No, there are cases where this doesn't give you the correct answer you are looking for. And finally, there is a negative vector. I mean, uh, it's the same as here. So for example, if I subtract u from both sides, so I have a negative vector. When I say u plus negative u, I get the 0 vector. And some of these we say, why are you listing these? But really, we need to cover all bases. So we make sure that what we have is a real vector space. Then we move to multiplication, and we have 5 more. Okay? So what in multiplication? So if I say number 6, there is also closure. But this one was closure under addition. This one is closure under scalar multiplication. Okay? So if I take a vector u and multiply it by a, b, or c, so if I say a times u, that stays in the vector space. It doesn't leave. I mean, there are examples we can give, but for example, let's pick something very common that is a very common example. If u is an integer number, okay, the like is the class of integers, is that a vector space? No, why not? Because if I multiply this u by a fraction, if a, we said a is real, right? So it may be, for example, 0.2. If you multiply 0.2 by 3, you get 0.6, which is not an integer. So you go away, you escape. You are no longer having the closure. Okay? Now, the scalar multiplication also is distributive. It's distributive and it's associative. So for distributive, I can say that b, let's say, since we used a, times u plus v is the same as b times u plus b times v. Okay? And then the associative, it's also associative. Meaning, if I say a times bu, this is the same as a times b, everything times u. Okay? So we did the distribution, we did oh, I think also the distribution between, so another distribution, maybe we should have written this before, would be again another distribution among the scalars. So if I say like a plus b times u, this is the same as a times u plus b times u, right? So whether it's one so one constant and two vectors, or one vector and two constants, you also have a unit vector, and you have so number 10 would be the unit vector, right? Unit vector. So if I take the number 1 and multiply it by v, I get back v. And these are the 10 axioms that if a vector or a group of vectors follow, then we call these vector spaces. And it's a very short introduction. We just need to know what a vector space is, because we will be using these throughout the rest of this course. Okay, so these 10 axioms, usually we have the two distributive properties before the associative, but it's really the numbering is, you know, very very subjective. You can list them in any order you want. But most importantly, I would say we need to make sure we have the zero vector in our vector space, and closure under addition, and closure under scalar multiplication. These are extremely important ones, especially if I take a part of this vector. So if I take a part of this vector space, we call it a subspace of it. So a small portion, I don't need to check all 10. I just want to make sure it's not empty. So it has the zero vector, and then it stays under closure, under addition, and under scalar multiplication. And I will make that just a very short session to give you an introduction, and then we'll talk more about these things in subsequent sessions. Thank you very much for watching. Hope to see you soon. Have a great day.